This is going to be a pretty short lesson. Limits are fairly easy, and if you crack open your calculus textbook to the definition of a limit section, you're going to get this nice little concise paragraph here. And let's read it out loud here. Okay? Suppose f goes from the reals to the reals, and that a and l are elements of the real numbers. It is said the limit of f as x approaches a is l, written like this here, if and only if for each epsilon greater than 0 there exists delta greater than 0 such that for all x minus a in absolute value is greater than 0 but less than delta, implies that the absolute value of f of x minus l is less than epsilon. So that's a lesson. There you go. That pretty much sums it up, I think, if you're reading your calc textbook. It makes some good sense. So for real though, that probably looks like Latin to you, and it drives me crazy that that's how they explain what a limit is right off the bat in most situations. So this is what a limit really says. Okay, it gives us a way to talk about what value a function is approaching as x approaches a particular value. Now that might not sound too exact, I guess, at this point in time, but after this lesson or after a couple other lessons, maybe come back to here and check that sentence out again. Hopefully it'll make some more sense. Okay, but it just gives us a way we talk about what a function is approaching as x approaches some value. So here is my first very super easy example. This says, as x approaches 2, the limit as x approaches 2, what is x squared getting close to? So if x is getting super uncomfortably close to 2, what does x squared get close to? So more mathematically, you might see it like this. As x gets infinitely close to 2, what does x squared get infinitely close to? And how it's read is, the limit as x approaches 2 of x squared is, and then you're supposed to answer that thing. And maybe you're thinking right now, well, if x is close to 2, then x squared has to be close to 4, and you're absolutely correct. But let's take a look at what's really going on here, because most of the time you're not going to get easy limits like this. So let's take some time to analyze this situation here. So here's the graph of x squared. You can see it's a nice little parabola, everybody knows that. And when they ask what's the limit as x goes to 2 of x squared, what they're really saying is, if you find where x is 2, that's right here, on this function, if we pick x values that are close to 2 from both sides, okay, and we bring them infinitely close together, so we're picking x values here and here, what y values are we getting back? So as I make x super close to 2, so let's put a little dotted line here, I'm picking x values in this tiny little window around 2. What tiny little window am I trapping my y values around? And you can see on this graph, if you make these x values super close to 2, well then the y values get super close to 4. The reason that's happening is because at 2, x squared is 4. Or basically, if f of x is x squared, then f of 2 is 4. Now this works out really simply because this is, again, an easy example to start off with. But the reason this works so nicely is because x squared has a property called continuity. Since x squared is a continuous function, basically what's going on here is, if we force x to be close to 2, then x squared has to be close to what it equals at 2, because it's continuous. So if x squared equals 4 when x is 2, then when x is around 2, x squared has to be close to 4. Not all functions behave this nicely. We're going to look at some examples where f of 2 could be 8, but around 2, f of x might equal like 3. So that's what we're going to get into, some crazy examples. But again, main idea, let's say this again. If x is getting super close to 2, x squared is getting super close to 4. So that's the answer here again. And we really don't care what's happening at 2. We don't care that f of 2 is 4 in this instance. I mean, it helps us out to solve the limit, but it doesn't matter if that happens or not. We care about what's happening as x approaches 2. So, if it looks so easy, why is it so difficult? Well, because the main reason is when with limits, we don't care what's happening at f of x at that specified value. So like I said with that x squared version, we don't care what's happening at 2. Yes, it equals 4, but we don't care about that. We care what it's approaching around 2. And around 2, it also approaches 4. And again, that's only because this function behaves very nicely. So, thinking about this in a little different light here, okay, it allows me to create some problems that are kind of scary. And I'm going to walk you through how I, as a calculus teacher, create some problems here, okay? So let's start with the function we're already looking at, x squared. So let's say I'm interested in you evaluating limits with x squared, but I want to make it difficult. I want to make x squared look a little bit scary. So what I'm going to do is this little magic here. I'm going to multiply it by x minus 2 over x minus 2. Okay? Now, these x minus 2's will cancel, so this still equals x squared, but it only equals x squared when x isn't 2. Because if you try to plug 2 into here, so let's say this is f of x. If I try to plug 2 into that, f of 2, well, now it's 4 times 0 over 0. Well, that's, first off, that's an ugly 4. That's 0 over 0. That's not a number. So now, let's go back again to that nice function we were looking at before. In this function, I can just plug in 2 and get an answer back, 4. Well, if the f of 2 is 4, then the limit has to be 4 as well. But now what I've done here, as a sneaky, jerky calculus teacher, is I made one little change. I multiplied by x minus 2 over x minus 2 to get this new function. Now when I plug 2 into that, I don't get 4. I get 0 over 0. Well, that's undefined. That actually is called something special. This 0 over 0 is going to be your friend, or maybe your nemesis, I don't know. But that's called indeterminate form. Indeterminate form. Okay, I'll squeeze it in down here. And it's called that because if you plug a number into a function and get 0 over 0, you cannot determine what's happening at that number. And that's what makes the limit so hard. We don't know what's happening as x gets close to 2 here just by plugging in 2 because we don't know what's happening at 2. We can't get a value back. So let me erase this for a second. Let me show you. I probably would not give my kids this function here. I want to give them x squared times x minus 2 over x minus 2. I'd probably multiply it out and give them this, x cubed minus 2x squared over x minus 2. That's what I would give them, f of x. And they'd have to simplify it down to this. Okay? So it is true that x cubed minus 2x squared over x minus 2, the top will factor to what it is up here. And then the x minus 2's will cancel, so it equals x squared. So we have this relationship here. F of x, which is this crazy looking function here, is the same exact thing as x squared, except for at x equals 2. So as long as I don't let x equal negative or equal positive 2, then this function here will be the same thing as x squared. And we can check it out. Let's go ahead and plug in a few values into these functions and show that they are the same thing. So let's get rid of this x squared here. Goodbye. Okay, let's plug in, I don't know, 2 into this. 2, that's one number we can't plug in. Let's plug in 1. If I plug 1 into f of x, we're going to get 1 minus 2 over 1 minus 2. Well, that's just negative 1 over negative 1. That's just 1. If I plug 1 into x squared, I get 1, same value. Okay, so that worked out. Let's try another one. Let's plug in, I don't know, some crazy number. Let's plug in negative 4. If I plug negative 4 into this thing, I'm going to get negative 64 minus 2 times positive 16 over negative 4 minus 2. So yeah, we got to do a lot of simplifying here. But what we're going to get is negative 64 minus 32 over negative 6. And what that equals is negative 64 minus 32 is negative 96. And divided by negative 6 is 16. You get 16. That's the same exact thing as if you plug negative 4 into x squared. You would get 16. Now, I only did that for 2 values, but I promise you, if you pick any value whatsoever and plug it into f of x, you're going to get the same exact thing as if you plugged it into x squared. That is true everywhere except for at 2. Because at 2, x squared equals 4. But at 2 down here, this is undefined. You can't plug 2 into here because if you do, you get 0 over 0. That's not a number. So our question is now that I've created this weird function that looks just like x squared everywhere except for 1.2, most likely I'm going to ask my students, hey kids, have a little bit of fun and tell me what the limit is here. What's the limit as x goes to 2 of x cubed minus 2x squared over x minus 2? And the very first thing they're going to want to do is plug in 2. So they plug in 2 and they get 0 over 0. I'm like, ah, crap. 0 over 0 means indeterminate form. That means I need to do some more work to simplify this down. Because, if you remember this from our simplifying expressions worksheets, if you plug 2 into a function and get 0, that means x minus 2 has to factor out. And if you get 0 on the top and bottom, that means both of them should be able to factor out on x minus 2, and x minus 2 should cancel. So, here's what you really do. You plug in 2, you get 0 over 0. You're like, crap. This isn't good. So you got to factor it out. So now this is no surprise. I mean, we already did this. This is how I got the problem. So we factor an x squared out of the top. On the bottom, we have an x minus 2, and all good. They cancel out. So I still want to know what's the limit as x approaches 2, but I can replace that crazy function with just x squared. And here's the beautiful thing about this. X squared is not the same thing as this function up here. It's the same thing almost everywhere except for one point, at 2. And that's the point that we're headed towards. But remember, with the limit, you don't care what happens at 2. I don't care what happens to this function at 2. It's undefined, that's good and all, but I don't care. I care what's happening as x approaches 2. So let's take a look at this graph. The answer to this is going to be 4, okay? So the answer is 4. But let's take a look at the graph. The graph of this function, x cubed minus 2x squared over x minus 2, looks just like the graph of x squared. Let's go back to the graph of x squared. That was right here. They look exactly the same, okay? Except for one point. At 2, there's a hole here. But again, we don't care what's happening at 2. We care what's happening around 2. So the question, what this is saying here, is if x is getting super close to 2, what's this function getting super close to? Well, look at this. As we bring x super close to 2 from both sides, super close to 2 from both sides, it's headed towards this hole. Now, when it gets there, there's no point. That's fine, though. As x gets super close to 2, my function values get super close to this value, which is 4. And that's exactly why the limit is 4. Now, if we didn't have a graph of this, we wouldn't be able to look at it and see that. Okay? Again, we're just closing in x values around 2, and that forces my y values to be closed around 4. We don't know that just by looking at this function, and when you plug in 2, you get 0 over 0, so that's a little sneaky. We don't like that. But if you simplify it down, you find out that this function looks just like x squared, except for one point, 2. And if x squared approaches 4 at 2, then this function has to approach 4 at 2 as well.